4.9, the last section in Unit 4, is about redox reactions, diving in a little bit further into those. We discussed a little bit about redox already this year at our Purdue field trip. We went to the electrochemistry day. Remember, we can define oxidation and reduction as oxidation is an increase in oxidation state, meaning it loses electrons, and reduction is a decrease in the oxidation state, meaning that it will gain electrons. So when we say moving electrons around, something that helps people is that when it's oxidation, the charge becomes more positive, and when it's reduction, the charge becomes more negative. Okay? So remember, we are using oxidation states, which we learned how to do in 4.7 for this. And sometimes it might actually be a charged compound. It might be just a molecular compound, but the same rules apply for those oxidation states. So metallurgy is the process of producing a metal from its ore. Always involves redox reactions. In the metallurgy of galena, which is lead sulfide, the principal lead-containing ore, the first step is the conversion of lead sulfide into its oxide, lead oxide. Then the oxide is then treated with carbon monoxide to produce the free metal of lead. For the reactions, for each reaction, let's identify the atoms that are oxidized and the ones that are reduced. So to do that, we need to assign all of our oxidation states, and we're going to do it for both of the chemical equations. Okay? So first of all, we know that anything by itself or a diatomic form is 0. So the O2 has an oxidation state of 0. I'm actually going to write that above the numbers. Sorry. And then in the PBS, the way that we're going to figure that out is we're going to use the charge of S as -2. So then that means that the PB will be a +2. Okay. Then on the product side, oxygen has a -2 oxidation state, so that means lead is +2. And then in the SO2, oxygen still has a -2, and there's -2 times 2 is a -4. So to balance that, the sulfur will have a +4 oxidation state. Okay, so to figure this out, we need to see the changes. So lead starts as a +2, and it goes to a +2. So that's no change. That's not going to be where the reduction happens, and that's not going to be the oxidation either. Okay? If it stays the same, it's neither of the two. Now the sulfur starts at a -2 on the reactant side, and it turns into a +4. So that is a change. So that's going to be one of our redox parts. Then oxygen, that's O for oxygen, starts out as a 0, and it goes to -2. Now it doesn't really matter which you choose because they're both -2. So it's -2 overall on that side. So that is also a change. So that tells us that one of these is going to be the oxidation and one of these will be the reduction. Well, the oxidation is the one that loses electrons or becomes more positive. And out of these two, the one that becomes more positive is the sulfur, because it goes from -2 to +4. So that means that the oxidation element is sulfur, and then the oxygen, sorry, all these words sound the same. Oxygen goes from a 0 to a -2, so it gets more negative. That means it's gaining electrons, so oxygen is the reduced substance. Okay, so that's how you would do it for the first reaction. Now the second reaction, we have PBO. Well, we just had PBO, so the oxidation states are going to stay the same. +2 for lead and -2 for oxygen. Carbon monoxide, CO, the O is -2 still, but the carbon, to balance that out, will be a +2. Then on the product side, lead by itself is just its elemental substance, so that'll be 0. And for oxidation state, and then the oxygen is still -2 in a compound. And so this time the carbon will be +4. Okay, so let's figure out the changes. For lead, it starts as a +2 and it goes to being 0. That's a change. That's going to be included. Oxygen starts out as a -2 and it goes to a -2. And again, it doesn't matter which one you do because they're both -2s. So that's going to stay the same. So that's not included. And then carbon starts out as a +2 and it turns into a +4. So the two that we're interested in are the lead this time and the carbon, because there is a change between those two. So the oxidized substance, I wrote that one first, we should probably say that one first. The oxidized substance is the one that is losing electrons, getting more positive. That would be carbon. And the lead, by default, would have to be the reduced, because, well, and also because it gets more negative. Okay? So that's how you would identify just which parts are oxidized, which parts are reduced from a chemical equation. Okay? You compare what it started out as a reactant, its oxidation state, and what it turns into for its oxidation state. And if there is a change, then it would be there. And you should only ever have two elements that change. You shouldn't have more than two elements change. And one should always go positive and one should always go negative. If you didn't get that, you did something wrong. To balance a redox reaction, oxidation states are used. You want to make sure that the number of electrons transferred is also balanced. It's the same as balancing the equation, but you just want to make sure that the electrons are also considered when balancing. Okay, so we're going to do, first we're going to follow these steps for example 13. Example 13 is very similar to what we did at our lab day, where we're going to write the unbalanced non-ionic equation and break it up into two half reactions. Then determine the number of electrons transferred, balance the number of electrons, balance the atoms, and add everything back together. Okay? So, we want to consider the reaction between copper metal and silver nitrate as seen. We want to balance the balance the equation using half reaction method. So, the first thing we need to do is we need to write the non-ionic equation. And that comes from getting rid of spectator ions. So, if you have a hard time seeing this, what I see right now is I see the nitrate grouped together exactly the same on either side. That is a hint that it's going to be a spectator ion. Okay? So in our ionic equation, we're going to get rid of the nitrates, but everything else stays. The coppers and the silvers, all ions and solids, stay as is. Okay? So let me rewrite it on this page. So that's going to turn into copper solid plus silver ion aqueous, and silver has a +1 charge, to form silver solid with no charge and copper with a +2 charge aqueous. So after we've written our net ionic equation, now we're going to break it apart into the two separate parts, right? Okay, so we're going to separate the coppers from the silvers. So we have copper solid turning into copper +2 aqueous for one of our equations, and then we have silver +1 aqueous turning into silver solid. Alright, so at this point we need to figure out how many electrons are transferred in each half reaction. These are both our half reactions, and then we want to make sure that the charges, the number of electrons match, and then we will add them back together. So for copper, it goes from a 0 to a +2. So that is 2 electrons change. And we're going to say we have to make the overall charge equal on both sides. And we're going to add electrons to do that. So if we added electrons to the reactant side, that would make it a -2 on the reactant side. And that's not what we want, because it wouldn't match the +2 from the product side. So instead, we're going to put 2 electrons on the product side to balance out that +2 charge. Okay, and then that makes an overall charge on the product side of 0. Now the silver, we have a +1 versus 0 for the solid silver. So that is a transfer of 1 electron this time, and we're going to add the 1 electron on the reactant side. Okay, now before we combine these back together, we have to have the number of electrons match, and it's 1 for silver and 2 for copper. So in order to make them match, we're going to multiply everything in the silver by 2. And I'm going to go ahead and rewrite this underneath the copper so we can see how they add together. Okay, so we have 2 electrons plus 2 silver ion forms 2 silver metal atoms. Okay, so then now we can combine these two equations together, and the electrons go away. They're on opposite sides, they cancel each other out, and that's all that cancels. So we have copper solid plus 2 silver ions makes copper ion plus 2 silver solids. Now this is it. This is good. This is a balanced equation because the atoms match. So notice how we have 2 silvers on either side. The charges match because we have an overall plus 2 on the reaction side and an overall plus 2 on the product side. So the charges on either side don't have to be 0. They just have to match. And that's what we're getting at when we balance. Okay, so that would be how you would balance that redox reaction. If you wanted to throw back in the spectator ion, you could. That would be copper solid plus 2 silver nitrates. It would still be balanced when you're done. To make copper 2 nitrate plus 2 silver metals. Now, could you have balanced that regular equation without going through all this trouble? Yes, you could have, but the point of a redox reaction is to see that transfer of electrons, so that's why we went through that part. The last example we have is an example of a redox reaction that's not in solution, but you still want to make sure that the electrons are balanced. So we want to balance the reaction between solid lead 2 oxide and ammonia gas to produce nitrogen gas, liquid water, and solid lead. So lead 2 oxide, PbO, because lead has plus 2, oxide has minus 2, solid, reacts with ammonia gas, which it's just NH3, to produce nitrogen gas, that's going to be N2 because nitrogen is diatomic, plus water, liquid, and solid lead. Okay, so in this problem, we can't do an ionic equation because there are no aqueous solutions as a part of this. They're all solid, liquid, or gas. So instead, we're just going to compare their oxidation states. So the oxygen we know has -2, so that means that the lead will have a +2. The nitrogen always has a +1. So then if there's 3 hydrogens, then that means nitrogen is a -3. N2 is diatomic, that'll just be a 0. H2O, H is +1, O is -2. And Pb is 0 when it's in solid form. Okay, so we want to still make sure that the charges are balanced out. Okay, so let's look at what we've got going on. Now, I'm just going to not waste my time writing it down. Do you notice how the oxygen stays -2 on either side? And the H, the hydrogen, stays +1 on either side? So that means that those are not considered in our redox part. Since they're not changing, their oxidation states aren't changing, then that is considered to just not be a part of it. Okay? But the lead starts with a +2 and it goes to being 0. And the nitrogen starts out as a -3 and it goes to being 0. Okay? So those are the parts that we're going to have to make sure that the electrons stay balanced. Now, looking at how many electrons are transferred, there are 2 electrons in the lead, and there are 3 electrons in the nitrogen being transferred. So we want to make sure that we have a total of -6 and +6 to help balance that out. So to get to be a -6, what we will do is we are going to multiply the nitrogen times 2 because it's a 3 and we want it to have a total of 6, -6 charge. So I'm going to put a 2 in front of the NH3. Okay. Hey, that also, by the way, balances out the fact that we have 2 nitrogens over here, so that's good. Then for the lead, we need a positive 6 charge, and we have 2, so we're going to multiply the lead by 3. So then that makes PbO have a coefficient of 3. Well, then we have now 3 leads, so we need to put a coefficient of 3 there to balance out the leads. And then last but not least, we want to just make sure all of the atoms are balanced before we're done. And we're missing something on the water because there are 6 H's and 3 oxygens, so we need to put a 3 coefficient on the water. Again, it just makes it a little bit more thought to your balancing of equations for redox to make sure that the charges also balance as you're doing that. But hopefully you understand the oxidation states after this section as well as 4.7.